Okay, today we're diving into a hidden war. It's a war being fought on a microscopic scale right now, inside billions of people and animals around the world. We're going to explore the absolutely brilliant science behind a very tricky question. How do you kill a parasitic worm without killing the person it's living in? So let's just start with the scale of this problem. What is this invisible enemy that's infecting over 1 billion people? I mean, that's a staggering number. We're talking about a whole class of what are called neglected tropical diseases, things that cause chronic, debilitating illness across the globe, but rarely, if ever, make the primetime news. The answer, of course, is parasitic worms, or helminths. And the weapons we use in this fight are a class of drugs called anthelmintics. And trust me, the way these things work is incredibly clever. So let's get into it. Right, so this is the central challenge, isn't it? How do you design a poison that's lethal to an intruder living inside of you, but is perfectly safe for you? The whole strategy, and it's truly brilliant, hinges on one single principle. And that principle is called selective toxicity. This is the absolute foundation of all modern anthelmintic drugs. This isn't about using a sledgehammer, it's about using a sniper rifle. It's not about brute force. It's about finding and exploiting a very specific weakness, a biological Achilles heel that only the parasite has. Think of it like a lock and a key. The parasite has these very specific biological structures, like these unique channels or specific proteins that are like locks. And here's the beautiful part. Our cells, human cells, we simply don't have those exact same locks. This allows scientists to become master locksmiths, designing a key, the drug, that fits the parasite's lock perfectly, while not even being able to slide into ours. And boy, have they designed an impressive arsenal of these keys. You can see here there are several major classes of these drugs, and each one has a totally unique way of attacking the parasite. For this explainer, we're going to focus on two of the real stars of the show, the benzimidazoles and the macrocyclic lactones. So, our first tactic, which is used by drugs like albendazole, is pretty wild. Imagine trying to demolish a skyscraper, not with explosives, but by methodically and quietly removing all of its internal support beams until the whole thing just collapses on its own. So here's how that works. The drug gets into the worm's intestinal cells. It finds a specific protein called beta-tubulin and latches on. Now, this protein is what the cell uses to build its internal skeleton, its scaffolding, called microtubules. By blocking that process, the drug prevents the cell from maintaining its shape. The cell structure literally falls apart, and when that happens, it can't absorb nutrients like glucose anymore. So the parasite is cut off from its food source and essentially starves to death from the inside out. And this part is just incredibly smart pharmacology. It's not just what the drug does, but how you take it. See, if you're fighting worms that are just in your gut, you take the pill on an empty stomach. That keeps the drug concentrated right there, in the gut, where you need it. But what if the parasite has migrated and formed cysts somewhere else, like in the brain? Well, then you take the exact same drug with a high-fat meal. The fat helps your body absorb the drug into your bloodstream by up to 5 times. It basically turns the drug into a system-wide heat-seeking missile. So clever. Okay, so that was the slow starvation method. Now let's pivot to a completely different and much faster approach. This isn't about slowly deconstructing the parasite. This is a direct, overwhelming neurological assault. It's a tactic that flips a switch in the parasite that can never, ever be turned off. And here we see the master stroke of a drug like ivermectin. It goes right for those unique ion channels we talked about before, the glue CLRs. It binds to them and basically jams the lock, forcing the channel to stay permanently open. This causes a massive flood of chloride ions into the parasite's nerve and muscle cells, and that influx completely short-circuits their nervous system, causing a total limp, flaccid paralysis. The worm is instantly neutralized. It can't move, it can't eat, it can't even hold on, so it just gets flushed right out of the body. And the secret to its incredible safety profile? Well, it's simple. Those specific channels, they're a feature of invertebrates, like worms. We're vertebrates. We just don't have them. So the drug has no primary target in our bodies. It is the perfect textbook case of selective toxicity. But, and this is a big but, the story doesn't end there. This is not a one-sided fight. The parasites aren't just passive victims here. They are in a constant, high-stakes, evolutionary arms race against every single drug we throw at them. So let's go back to our analogy. If the drug is the key and the receptor is the lock, what happens when the parasite literally evolves to change the shape of the lock? Well, that's what we're up against, and it introduces the single biggest challenge in this field today: drug resistance. A key that was a perfect fit yesterday might not even turn in the lock tomorrow. To see how this works, let's look at a real-world example. It's called the G36A mutation. It's a tiny, tiny change. Just a single amino acid, one little protein building block, gets swapped for another in the worm's receptor. I mean, it's a minuscule alteration at the molecular level, but that one tiny change is enough to make the lock work completely differently. And the real-world consequence of that tiny molecular change? It's enormous. Just look at this chart. The drug's efficacy completely plummets. In the original, wild-type parasite, it's almost perfectly effective. But in the mutant, the resistant one, its power is just drastically reduced. So what researchers found is that the mutation does something really subtle. It doesn't necessarily stop the drug from binding to the receptor. Instead, it changes how the receptor itself behaves. It makes the channel close much faster and become less responsive in general. So the key might still fit in the lock, but the lock is now wired to resist being opened. The effect the drug has is just much weaker. So the big takeaway here is that the parasite hasn't just built a shield to block the drug. No, it's done something far more sophisticated. It has fundamentally rewired the very target of the attack. And you can imagine, this makes designing the next generation of drugs so much harder because we're aiming at a target that is constantly moving and changing its own internal wiring. And that leaves us with a critical and honestly pretty profound question. This battle is far from over. It's a continuous contest, pitting our best chemical ingenuity against millions of years of relentless natural selection. And how our science evolves to meet that challenge will quite literally define the future of global health for millions and potentially billions of people.